and share it to everyone, because I think the YouTube side tends to be fairly popular.
Yeah. It would also be a good idea for me to actually open this link.
Yeah. I'll send it to you on Zulip.
Yeah, I actually can just copy paste it out of the.
I'll put it there just just for anyone else at Ferrous to take a look. And let me pull it up.
Yep.
Okay. Do you want to tweet from the Rust Analyzer account, and I'll retweet from Ferrous?
Okay. I can actually see myself.
I'm gonna hand the host back to you. You also might want to go into participants and right-click on your own name, and change your name to not your email address. So you go
Oh
to
my god,
participants.
I cannot do Twitter. Tweeted?
Tweeted. Okay, let me find. Retweet from all of the sources. Okay, then I'm probably going to drop out. I'll keep an eye on the YouTube stream, and I guess ping me on Zulip if you need anything.
Yeah, sure.
Okay. Well, enjoy the stream, everyone.
So we have a couple of minutes more until we are officially starting. If you want to ask questions, you can ask them either via Q&A button in Zoom or via the YouTube chat box on the right. So, I guess it's about time to start. My name is Alexey Kladov. I work at Ferrous Systems, and I do there, and actually I have been doing for some quiet time before that, various IDE-related things in Rust. Originally, I worked at JetBrains, where I worked on IntelliJ Rust platform, and now I'm doing this experimental Rust analyzer project, which hopefully will bring us perfect IDE experience someday. Yes, there was a question on YouTube. So whether this is a Q&A about general IDE support or Rust Analyzer. I guess it is kind of like about general IDE support, because I'm very familiar with Rust Analyzer and with IntelliJ Rust, and somewhat familiar, but although not to that extent, with Arrowlights as well. But I probably am going to focus on Rust Analyzer primarily, because, well, that's what I'm putting my working hours in, and that's what I believe, hope, and dream is the future of Rust IDEs. Yeah, so I hope you start shouting your questions at me, either via Q&A section in Zoom or via YouTube video. And I think I've got one question on Reddit about kind of like relationship between Rust Analyzer and IntelliJ Rust, and how do they compare in terms of features, and basically which one should you use if you want to use an IDE in Rust today. First of all, I must say I'm kind of like really the wrong person to ask this kind of question, because I kind of like biased both ways, as I worked on both Rust Analyzer and IntelliJ. But I would say that today they are generally comparable. Like, they are wildly different, and they have wildly different architecture and implications and that sort of stuff. But in terms of user experience, I would say that, like, on the like highest order of magnitude, largest level, they are pretty similar. You get completion, you get code definition, you get various refactorings, and all those things are based on kind of similar architecture of IDE, based on full fidelity syntax trees, which preserve white space, comments, and that sort of stuff. That's it. The primary difference between IntelliJ and Rust Analyzer is that IntelliJ is very much a part of IntelliJ Rust is very much a part of IntelliJ platform, and this is a huge benefit because IntelliJ Rust leverages a lot of language functionality built into IntelliJ. Like, for example, the parser, which is used by IntelliJ Rust, is written using the parsing library from a platform. The parser for Rust Analyzer is written from scratch. So kind of more effort to do stuff in Rust Analyzer. But at the same time, the IntelliJ Rust currently exists only as a plugin for JetBrains products, while Rust Analyzer is a language server. So it is a separate binary which exposes so-called language server protocol, which is a simple JSON RPC text protocol. And in theory, any editor can connect to Rust Analyzer and get code completion, go to definition, and all other fancy IDE stuff. And this in theory part is, I think, kind of pans out in practice, in that I personally do think that this code is the editor which supports which is supported by Rust Analyzer the best, but most of the features work in Emacs and Vim as well. But for some less popular editors, the support is definitely more supporting. So yeah, that's kind of like the big difference. And if you want to use IntelliJ product because you are familiar with those IDs or because you find them better. And I actually personally find IntelliJ editor more convenient for me than VS Code. Then, well, you should probably use IntelliJ Rust. If you want to use any other editor, I would suggest either try IntelliJ Rust or RLS. I would probably say that IntelliJ Rust is kind of better than RLS. It definitely is better for my own workflow, and I've heard a lot of people say that it is better for their workflow. Though here, as usual, it is better to try things out than to just blindly trust someone's opinion. Yes, so modular is like big kind of like Kotlin versus Rust implementation detail. The two projects are kind of similar, and sadly at the moment they both re-implement effectively a major part of Rust compiler from scratch. But for Rust Analyzer, we have like this grand libraryification plan that someday we will actually merge the Rust Analyzer implementation, which is geared towards being fit for ID purposes. That means it is like kind of slow, but also is very lazy. I probably should go over this separately. And the Rust implementation, which is very mature production implementation, whose primary purpose is like command line compiler, the use case where you don't need to give like completion instantly, but where you have to compile a ton of code as fast as possible. So yeah, kind of like in theory, Rust Analyzer is better in sense that we will be able to share code. In practice, the amount of shared code today is pretty negligible. Specifically, only the lecture is shared between Rust-C and Rust Analyzer. And we are kind of like thinking and starting with sharing the parser code, but that is, well, complicated, and it would be quite some time because before that sharing actually pans out in practice. Yes, so that's, I think, the second fundamental difference is that for Rust Analyzer, we kind of have hope that initially, that eventually there would be like just Rust-C, which could be used either as a command line compiler or an IDE. But for IntelliJ Rust, well, it also is possible, but we would have to rewrite our compiler with Kotlin, which I don't think is necessarily a terrible idea because Kotlin is also a pretty nice language. I think the third fundamental difference between IntelliJ Rust and Rust Analyzer is, well, it kind of like fundamental on the level of ideas, but the actual implementation is like more similar than not, but nevertheless. For IntelliJ Rust, the explicit purpose was to build an IDE and to kind of like compromise sometimes on correctness to give useful results to the users faster. Like, for example, to implement wrong go to definition if it is right most of the time. In Rust Analyzer, as we want to become part of the main compiler, or like just the main compiler eventually, we try hard to, well, at least we try hard to make sure that everything we write could, in theory, be extended to absolutely correct implementation. it's definitely true that rationalizer has like a huge amount of bugs, and not like even bugs, but where we like do something silly and completely contrary to language reference just because it is like much simpler, and the probability that you actually hit this in real code base is pretty low. That said, it's generally works like a real compiler, and the most fundamental bit where like IntelliJ and rationalizer approach diverge internally is the approach to name resolution. I guess probably is some time to show a little bit of the code there. Surprisingly, there are 3 questions and answers in Zoom, which I've completely missed because, yeah, Zoom doesn't show that there are questions and answers. At least you actually hover over the thing. Okay, let me quickly skim from that. Thank you, John, for questions. I think I will get them in a little bit, and actually like this explaining of fundamental difference between rationalizer and IntelliJ with approach to correctness is kind of part of the answer to this question. So just to like make this probably a little bit more fun, let's look at some code. Share my screen. Okay, hopefully you see the screen. And we now go to the code which handles name resolution rationalizer. Yes, it is here. And we want, yeah, I guess that's it. And here there should be this. Yeah. So what's the big deal in difference between rationalizer and IntelliJ? Actually, this kind of simple and short loop. So what is this bit of code we are looking at? It's name resolution. Purpose of name resolution is to handle things like this. Like if you have 2 modules and you have a struct in one module and in another module you have a use for this structure, name resolution needs to figure out that if we write a function here which uses this name bar, then it actually is this name bar in that other module. And the problem with Rust is that the rules for finding, for resolving use items in particular, are pretty complicated. Specifically, you can do things like this. Like let's here import bar as bars. And here we pub use superbars as quacks. And here we like also use bar quacks as z, and here we return z. And yeah, actually typing this inside the function is a bad idea because we don't run name resolution inside the function fully yet. And this is one of the limitations. But let's put this on the top level, and yeah, now it kind of visible that I actually made quite a bit of typos. So yeah, rationalizer correctly enforces that if I press go to definition on this z, I get to this bar. And let me quickly check if someone complains if like the font is too small or whatnot. No, nobody complains about the font, but let's still zoom in a little bit. Okay, so it should be better now. Yeah, so The problem here is that to figure out the meaning of this Z, you kind of like need to start to resolve this in part, but it actually refers back to the original module. So then you have to resolve this in part and support this type alias. And in general, like this process of resolving an import is not a simple question of finding a struct with a specific fully qualified name, in that imports are allowed to be circular. And especially if you add macros and glob imports into the picture, you really get this situation where you kind of like have sea of modules, and modules import names from each other, and one module may publicly reuse imports from another module. And the way you want to handle name resolution is that if a new name appears in a module from, for example, the expanded macro, this name should propagate to all the modules which re-export all the items of the module. So kind of like the idea is that you maintain a set of names visible in each module, then you add a new name, and then you propagate this name to all other modules. And you repeat this procedure recursively until there is no more changes. This is so-called fixed point iteration algorithm. And here it is written in Rust Analyzer, well, at least like the main driving point in it. We try to resolve some imports, and then we try to resolve some macros. And unless we figured out that no new imports or macros have been resolved, we loop around and repeat this procedure until we reach a fixed point. And yeah, I kind of feel that this style of name resolution is the only way to give to get 100% correct results, to get the same results which RC itself is getting. And that's why this algorithm is implemented in Rust Analyzer. In IntelliJ Rust, we've at least initially, I think there are plans doing something smarter right now, but at least initially we went deliberately with a much simpler recursive algorithm, which basically sees an import and like tries to work the tree of module resolving a name one by one, which works surprisingly good in the majority of use cases, but still kind of impossible to make 100 correct precisely. So yeah, that was a very long-winded and specific explanation about what is different between IntelliJ Rust and Rust Analyzer approach in the like grand philosophical differences. And that Rust Analyzer tries to be, at least in theory, capable of being 100% correct. And this actually goes to another question is that there are a lot of cases where, while in theory Rust analyzers should be like correct and great, etc., in practice it actually falls down and does not give you any kind of completion. Just find some case in here. It shouldn't be too hard. Yeah, this actually works. Yeah, and this is the case where kind of like, in theory, the theory is great. In practice, we get no useful completion out of this closure. And the reason for that is that, well, Rust analyzer cannot infer types for this directive local variable. If it were able to do that, there would be a type hint here. If we actually add the type, we get the completions, but the type is not specified and neither can figure it out, so we have no completions. The general answer here is that, yeah, Rust is kind of a difficult language, and given that most of the implementation is separate from the compiler, we have a lot of cases uncovered, a lot of cases not covered. So yeah, sometimes things do not work, and what makes this kind of like extremely frustrated from the user's point of view is that if you have a large expression and one part of this expression does not work and Rustlizer cannot infer type there, it usually means that like this unknown type propagates outwards, and eventually like the whole expression is of unknown type, and you don't get type errors, and you don't get completions, and that is frustrating. My understanding that the biggest source of these false negatives today is a particular issue in our support for traits. Specifically, we sometimes cannot infer types correctly when associated types are involved. And in this case, the associated type is involved because the type of the item of the iterator is associated. And this actually is very curious. Why? Because this code, which deals with associated types, is not actually a part of Rustlizer itself. It is part of the Chalk project. And the Chalk project is, on the one hand, an experiment in implementing an alternative trait solver for Rust to unlock new features like generic associated types or whatever type features we want from traits. I don't actually remember any one except associated types, generic associated types. And yeah, the second goal of Chalk is have some trait which can be shared between Rust and Rustlizer. And the fun thing is like Rustlizer already is using Chalk and has been using it for some time in production, but Rust still uses the old trait solver, which is gets into kind of a heart of this problem with like libraryification, is that it's not that hard to write a library. It's not that hard to integrate library into Rust Analyzer. What really is really difficult is taking an existent library, which is like dormant inside Rust C and is spread across multiple modules, and is basically like a cement which glues all the pieces of Rustlizer of Rust C together, and extracting that piece outside and replacing that. As usual, writing new code is much easier and more enjoyable than doing something useful with the variable code you already have. Okay, so this bit about associated types comes from Chalk, and it actually is a Chalk problem that Chalk cannot properly infer associated types. I absolutely don't know any like details here because, and this is super exciting thing about Rustlizer, is that although I kind of like started the project, all the smart bits, everything about type inference, everything about traits is currently handled by this Floodibolt contributor, who I think it was last Christmas just sent a PR to Rust Analyzer saying, hey, I was bored, so I like implemented a type system. So here, there's working type system. Like super excited, and without Florian, definitely Rust Analyzer wouldn't be a thing. So thank you, Florian, for making this happen. And yeah, if type inference does not work, ask Florian, not me. So yeah, the core issue is that Chalk is at least currently not capable of solving required trace queries here, but Florian actually is working on a new recursive Chalk solver. Well, I think like the current one is also like recursive and does fixed point and or whatever logical programming shenanigans you need to do to solve traits. But the new solver is officially called recursive, is I think is similar to what RC is doing currently, and in theory it should be able to solve this problem. And this is actually a really cool benefit of this libraryification, in that by extracting Chalk as a separate and somewhat well-defined interface, we are now able to experiment with various solver implementations rather flexibly, in that you can hack on Chalk as an isolated project. You don't need to build Rust C to hack on Chalk. You don't need to build Rust Neither to hack on Chalk. It defines its own kind of like intermediate representation, and you can work fully on these logical level programming layer. Yeah, so to sum up, we absolutely do miss types in a lot of cases. And actually, I think this might be the case where IntelliJ Rust is currently ahead of us, because I think IntelliJ handles iterators and closures better than us at the moment. Nevertheless, there is one specific issue in Chalk which is responsible for a huge amount of loss false positives. And there is already an in-progress pull request in Chalk repository to solve this issue. Just like put the link to the PR here so that you can follow along if you are into these kinds of things. Yeah, so I've posted the link to the PR to the YouTube stream. And hopefully it will make code completion better, or at least it will like uncover the next 90% of all kinds of type errors. Okay, so I guess that answers the question about missing completions. What are the roadblocks for completions? Basically, this Chalk issue, and I expect that after we tackle Chalk, the next big thing would probably be support for procedural macros. However, another awesome contributor to Rust Neither, Edwin Cheng, is doing all the macro work. And in particular, right now, they are experimenting with integrating procedural macros into Rust Analyzer. So hopefully, we will be able to solve both Chalk issue and procedural macro issue in more or less the same time frame. Probably at some point it would be good to get into a little bit more details about the upcoming procedural macro support, because it's kind of like a fun architectural problem, but I see a lot of questions here, so let me just quickly answer them. Okay, good question from EH 2406. Is there something we could do in addition to make name resolution easier? That is a tough question. My gut feeling is that unfortunately we won't be able to do that for the simple reason that we need to support old editions. And like, even if we have a simpler name resolution algorithm in the new edition, we would still have to have this fixed point iteration loop for edition 2015 and 2018. So we won't be able to remove any kind of complexity from the Rust IDE unless we drop support for all the editions completely, but that is clearly not on the table because stability is more important than IDE support. That said, there probably are cases where we can tweak name resolution to be more helpful for IDEs. In particular, another horrible issue happens is that in Rust currently you can have a function, and inside this function you can have an impl block without completion because we don't support that, sadly. And in this impl block you can define a function, and then this function will actually be visible outside. Let me just quickly compile it to see if this actually parses Rust C, because in Rustlizer we don't support this, so obviously like go to definition doesn't work and falls back on stupid index-based lookup. But nevertheless, yeah, as you see, the code compiles. And this is horrible for IDEs, like really. And I think actually like maybe not even for IDEs, but also for humans as well. Because that means that you can write something inside a function which has effect outside the function. So to like understand the code completely, you need to look into to understand code of a single function, of like this function completely. You actually could need to look into bodies of every other function, because for example, here we are like calling a file id.into method, and it looks like it calls an into trait, but it actually might be an inherent method on file ID if there is an impl which defines this inherent method. And this impl might be buried somewhere inside a function, so we need to parse every function. In Rustlizer, we currently parse and analyze function bodies lazily in general. We only infer types in functions in the currently open files. For all the files which are not currently open in the editor, we parse and process function headers. We learn about each function, we learn about its arguments and its return type, but we don't look inside function body. And that is a pretty crucial optimization for IDEs, because most of the code lives inside bodies. And if you don't look into most of the bodies, that means that the total amount of data you have to process inside IDE is much smaller. So the IDE can be faster, more energy efficient, and whatnot. In theory, in practice, yeah, as we see, Rust currently allows certain constructs which escape this very strong boundary of function body. First one is inherit impl. Second one is like the usual impl. You can write something like this, and it will like totally be globally visible. And the third construct is micro export. Export. You kind of like define this macro inside a function, but then make it visible outside the function. For this thing, I actually do believe that we can do something in the addition boundary. In particular, we can like outright forbid this kind of crazy code. And for this code, we actually don't want to outright forbid it, because it is pretty common sometimes to do something like define a structure inside a function and then write a local impl for the structure, like blah, 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 blah. And yeah, that's useful pattern to have. And it's actually kind of like not problematic for an IDE, because, well, we need to understand the body of a full function to get the methods of the point. But the point struct itself does not escape a function. So if we have a point, we already are parsing this body, and it's not a problem to just look at it. The solution I'm thinking about here is to treat these treat function bodies as downstream traits from a coherence point of view. In that each function is kind of a small mini crate, and you can only write an impl inside the function if this impl would be allowed by the coherence rule. And that actually gives us the property which we want. Impulse in downstream crates in Rust do not affect upstream crates, which would be crazy if it would be otherwise, because if, for example, you don't know, you publish a library on crates.io, you would need to parse all dependent crates of your library to like make sense of what it's doing. It's like crazy. With coherence, we know that, okay, all the impulse we know are either in our crates or in dependencies. And yeah, if we do this, in addition, that would make it possible to write a more performant IDE. Surely, for the old crates, we would have to fall back on this mode of parsing function bodies fully, but for crates which actually make use of this new addition, we can have a more efficient implementation. And what actually is the most hilarious here is that, well, if we do this properly, like an addition requires us, this needs to be some kind of a lint, because we cannot just like introduce breaking changes without any warning. And as a lint, this lint would need some way to silence it. So we can imagine something like allow, I don't know, leak an impulse. And the cool and funny bit here is that the act of allowing this lint itself makes the problem go away, because now the IDE can see the attribute outside of a function and can understand, hey, this single function I need to parse and need to take the implementations there into account. Of course, it does not work if you like do just a blanket allow on your whole trait, but that crate, but that just means that IDE will be slower for your crate. So yeah, it's interesting, but also it's kind of like really, really, really far in the future. We are definitely not at a point where doing this is practical. There are much more lower hanging fruits to be had with librarification efforts, like making Chalk a part of both RustC and Rustanalyzer, and like sharing parser and that stuff. But still, in like RustC 2092, maybe. I don't know. Okay, I would consider this question answered. The next question. Is there a module or library in Rust Analyzer that provides a linked view of the source code? Like a view where you can like take an identifier and see what this identifier means, to what actual name it refers. Basically, kind of like scene API, but also with access to type information and name resolution and whatnot. So that's kind of the whole point of Rust Analyzer, is to provide this kind of linked view of source code, because an IDE needs this feature to do its IDE stuff. So for example, let's see how some simple feature is implemented. My favorite one, fill match arms. If you're wondering why there is no index highlighting here, is that because Rust Analyzer takes some time to highlight the code, and I deliberately use by default a theme which does not color code at all, so that I can see bugs in syntax highlighting, so that I'm sure that it's like Rust Analyzer colors something wrongly, and not that my color theme is acting weirdly. Okay, so this is fill match arm expression extension, expression extension assist. And what it does is that if you have code like enum and you have a function, I wonder why I don't get syntax highlighting here. It seems like it might be bad. No, it's working. So if I have an enum and I match this enum, there is this useful fill match arms helper. And if I press it, I get, well, the template for my enum. And it's, I think, as of recently, let me check this, actually works with tuples. Yes, it even works with tuples. It's like amazing, amazing technology. So yeah, and obviously to like this kind of feature, we not only need to understand that there is a syntax of a match expression involved, but we also need to understand the semantics of this match expression. We need to understand the type of the expression we are matching against, and then we need to understand that this type is actually an enum, and based on variance of this enum, generate the match arms. So this is exactly what happens in Rust Analyzer. Specifically, like all the actual type inference is implemented in the like so-called compiler part, which is called here like high-level intermediate representation, for really 0 reasons. Like name HIR in Rust Analyzer does not make any sense, except that it is like a short acronym. So it's just a combination of letters. So this like here is actually a compiler, and it is implemented in terms of like very low-level things. The problem is you're writing and like it's implemented in terms of like low-level things, because the job of these crates is to compute the information. Like you have some type info, and you kind of like do some additional processing on it, and you get more type info in the end. So kind of like the code in the compiler is in semi-analyzed state. You know some facts about it, you don't know other facts about it, and you are deriving these new facts using old facts. When you are writing an IDE feature, and fill match arms is purely an IDE feature, you actually don't care at all how those facts are derived. You really want to see like a static view of code, like a code which is fully annotated with types, with reference, with whatnot. You, as if like something just tells you. So internally in Rust Analyzer, there is this facade pattern in the create array here, or here, I don't know how to pronounce here, which kind of like shields or rather separates this in-progress computation in Rust Analyzer and the view of linked code in the IDE part. Actually, I actually like the name linked code. I wonder if we should just like rename this concept to linked code, because it seems like it kind of makes sense, except that it's also very confusing with the actual process of like linking in the backend of the compiler. But whatnot. And so, yeah, just let's quickly walk through how this facade. So this charts is an assist, and it starts with a knowledge of syntax. I'll just copy this example to be more illustrative. So like assist starts with basically only a cursor position in a file, and it needs to figure out what to do. What assist first does is that it parses the file and figures the syntactic the syntax as a cursor. I actually can look at the syntax in Rust Analyzer by using show syntax tree extension. So here we kind of like can hover over various nodes and see where they are in the syntax tree, which is a super cool feature. I'm glad that another contributor implemented it. I've never thought I actually would need this, but yeah, now I use it almost every day, and it makes me not sure if more productive, but definitely more happy. Okay, so we start with like a syntax, and we find the particular match expression at the position of the cursor. And this match expression is just the syntax. It is something which you could get from Syn, for example, although we use slightly different API because we allow for everything to be optional to allow representing incomplete node. The next thing you want to do with this syntax is to get type information. And for that, we get this semantics type, which we abbreviate SEMA for local variables. And this is kind of like the struct, which represents the facade between compiler and the IDE. And this semantic type has all kinds of, let me fold it so that I can only fold level 2. Yeah. Has all kinds of like methods to get information about source, like this links. For example, we can feed it of the expression, and it will return us a type which this expression has in this particular context. And inside this semantics, it's like just not really complicated type itself. It just calls out into like type interface machinery, and that machinery is where like all the actual crazy magic happens. So yeah, given the semantics, we feed syntax, we get back type. No, we don't use type of here. Yeah, it's like slightly hidden in a separate function for whatever reason. Yeah, we get the type of expression. Oh, and auto reference is involved, but anyway, we try to compare our type with abstract data type or a data type, which can be an anom, a struct, or a union. And if it's an anom, we return this anom. And like having resolved type of expression to anom, we can actually construct the list of missing arms and then do some syntax tree manipulations to actually insert the match arms. So to sum up, is there like an API in Rust Analyzer for viewing linked code? Yes, it certainly is. It is very much one of the central architectural divisions in Rust Analyzer because it like separates the kind of like what I want to see in Rust C eventually from what I want to see as a like purely IDE part. This boundary is kind of fuzzy at the moment, and the API is horrible and like undocumented and absolutely definitely 100% not stable. Although Rust Analyzer itself is absolutely a stable crate, although it's not published on crates.io. So if like you want to do some analysis of Rust code today, you can, for example, use Rust Analyzer as a Git dependency and use this SEMA analysis, and it will work and it will be able to stable compiler. But of course, next week we will change the APIs completely, and you will have to rewrite your code if you want to keep up with it. But you can also kind of like pin a specific version of Rust Analyzer and never update your code, and that would be working forever because Rust itself guarantees that it is not going to make breaking changes. So yeah, this linking code concept exists internally. It's a fuzzy concept. I really, really, really want to make it a lot more crisp to make like real intermediate language out of this linked code, and maybe in like far future even make this linked code some kind of like semi-stable API of the compiler to allow third parties to extend the compiler and the IDE, but that's pretty far at the moment, unfortunately. That said, actually, this was one question on Zulip today. If you really want to use Rust Analyzer for kind of like some kind of analysis or transformation in your project, I suggest trying this out by cloning Rust Analyzer and implementing your code is as this light bulb assist to just get a feeling if you, in theory, could use it or not. The assists are in array assist rate, and hopefully, although like as almost everywhere in Rust Analyzer, like amount of documentation is like negligible, it should be possible to look at the examples and to understand roughly how to manage with syntactic and semantic information and do something useful. And yeah, if you can implement something with the assist, then Rust Analyzer will get the UI bits implemented for you, in that you would be able to apply this assist in the IDE using shortcut, and you will be able to apply the actual syntax changes automatically. So yeah, it's good way to experiment with extended Rust Analyzer. Yeah, actually, I have been answering this question this whole time. Okay, there are a lot of questions, and I am going to continue answering them. But right now, I think I need a short break, or let's say about 5 minutes until 58 minutes to like drink some tea and stop talking for a moment. So let me stop sharing my video and audio. And I will be back in 5 minutes. Yes, probably needs to write about this. Okay, see you in 5 minutes. Okay, so let's continue. Before answering my next question, I kind of like want to do a shameless self-promotion plug in that, well, I work at Ferrous Systems and we are a consulting company. So we can help you with trainings, with making your more efficient with using Rust, and in general, like with like basically anything Rust related. And in particular, we have this Rust experts service, which is kind of like consulting light, in that we don't literally come on the premises, but we give you access to our experts. Basically, you can shout answers, shout questions at me or James or other folks at Ferrous, and we will answer you using our collective knowledge. We typically do it via Zulip. And this actually kind of useful way to do consulting in the present situation. So we are running these Q&A sessions as part of promotion of the service. And we also have discounts for the service. So if you're interested, or if you are not interested but just curious, please take a look at the details in the YouTube channel. Let me just check that I am not muted and go to the next questions. What algorithm are you using for type inference? Good question. I don't know the answer, honestly. Florian is the main expert on Rust inference, but I would say it kind of like the same algorithm that Rust C uses, and it can be described kind of like as a Hindi Milner with a twist. So there are kind of like two big families of type inference algorithm. One is in like pre-type inference, pre-lambdas Java, when you just annotate a variable and every parameter explicitly with type, and you infer types recursively. For example, like the type of expression you get from the types of sub-expressions, and you don't look at the bigger context at all. You basically like do the whole type inference via like one pass top-down walk through the syntax tree. The other type inference is so-called linear type inference, like in Haskell, where, at least in theory, you sort of do type inference in two passes. And you do it in two passes and not in one pass, because you actually don't specify types of local variables and function parameters. And what these two passes allow you is to infer those types. So how Hindley-Milner works in general is that it works the tree top-down, and it records equations about types. It does not actually resolve types, but it says like, hey, we are calling this function with this variable, so the type of this variable must be comparable with the type with the type which this function accepts. And if the function accepts a specific type, like foo, then we know the type of variable exactly. However, the function can also be generic. It can, for example, accept the tuple of two t's. So we know after this constraint is added that like our variable should be like a tuple of two types, but we don't know types itself. So we cannot infer types fully, and for that reason, we like just accumulate constraints. And after we have accumulated the full set of constraints, we run a so-called unification algorithm on these constraints. And what this unification algorithm does is that it finds assignment of types to local variables, which satisfies all the constraints. And yeah, that's, I think, called algorithm U or something like that. basically some specific interesting but kind of black box algorithm. The problem with Rust, of course, is that it's like a fancy, complicated language, and it actually uses neither of the two approaches. So it uses kind of a weird mix of the two, in that it walks a function top-down, it collects the constraints, but instead of resolving the constraints only at the end, sometimes Rust tries to resolve constraints in the middle of a function. In particular, if you, that would be a good example. So here, the type of match expression is match expression. It's a funny thing working with like this compiler stuff is that kind of like you have a struct called struct, and it's just recursion all the way down. So the type of match expression is match expression, and in the next line we like call the match arm list method on this expression. And this works because the type here is kind of like specified explicitly, because here we use the turbofish, but we also like can replace turbofish with an explicit type. Actually, do we already have an assist to like do this automatically? Can I like Alt enter here and say no? Yeah, that's actually one feature which you might implement in Rust Analyzer. Make an assist such that you press Alt enter here and the type goes to the right hand side. We have just insert explicit type here, but it does not remove the old type, and it also should actually add ISD here, which probably is a bug, but nevertheless. So yeah, here we like can know what this method refers to. However, if we erase this assignment, Rust Analyzer will stop knowing the type here, and what's more, even Rust C will not ensure types here and complain that, hey, the type is unknown and you need to constrain it. That is like the difference, the primary difference in Rust C from the like typical Hindley-Milner inference, is that when it comes to method calls and fields assist, fields accesses, Rust requires the types to be fully known. So at this place, Rust will take the set of constraints accumulated so far and will try to solve it. And if there is like a unique solution, it works. But if there isn't a solution, it will complain that, hey, I need more type annotations here. I'm not sure if there is like any specific name for this type inference algorithm. It's generally kind of like a Rust C type inference. And of course, another twist here is that actually figuring out what this method calls refers to is like hugely intricate, because it depends on the trade system and various rules for which impulse apply when, etc., etc. But it also is kind of black boxish from the purpose of type inference, is in that type inference figures out this type and then just asks the type inference engine, the trade solving engine, like, hey, I get this type and I'm trying to call this method on this type. So please tell me which trade this method comes from. Yeah, that was the answer to the question, which algorithm is used for type inference. The question about the example a way back about local impulse, like if we have struct foo and we have fnf and we have impl foo, and here we have method foo. The question, wouldn't this method be visible only inside function f? And the answer is no, it absolutely is visible outside. Like I can run cargo check here, and cargo check will only complain that the function itself is unused. It won't complain that this is an unknown method. So yeah, local methods are indeed visible globally. Yeah, a fun question. Why Rustanalyzer uses so much RAM? I have a hello world, and Rustanalyzer consumes 140 megabytes of RAM. That's a really good question, and indeed is I think one of the biggest kind of like architectural problems with Rustanalyzer at the moment. So where the memory usage comes from? It comes from two primary sources. First of all, Rustanalyzer. Let me quickly recheck that I indeed want to say two things and not one or three. Yeah, two things. First of all, Rustanalyzer currently analyzes the crates from source. It does not use the RLibs produced by the compiler. So for example, if you reload Rustanalyzer, it would take quite a while before Rustanalyzer loads, and then even more time before it actually shows you first completion, or before it actually shows you the syntax highlighting for the first time. Syntax highlighting, kick in. Actually, I'm not sure why syntax highlighting still is not on, because we see completion. So this means that we've already processed this. And yes, I want syntax highlighting here. It actually, yeah, finally, probably was some kind of like client-side bug, because if we like the amount of info you need for syntax highlighting is roughly the same as the amount of info you need for completion. So we should show them at the same time. Yeah, as you see, it kind of like took, well, 10 seconds maybe to like load and process this file. And the reason for that is that we really analyze every crate from source. So during these 10 seconds, Rustanalyzer processed the standard library using the sources of standard library and not the compiled version of standard library. It processed the crates IO dependencies of Rustanalyzer, again, using the sources. It processed all other crates in Rustanalyzer workspace. And finally, it processed this specific crate. Doing this from scratch definitely takes time, and it definitely takes RAM as well. Because after we analyze this whole set of things, we need to somehow keep them in memory and to be able to update them incrementally. And that is one of the biggest difference with RustC, because RustC lives in this very narrow one crate at a time world, where RustC only looks at a single crate, and all other crates exists only as binary RLib files, which contain metadata. Rustanalyzer needs to work with multiple crates. It is possible to imagine like a single crate mode for Rustanalyzer, and this, for example, how RLS initially worked, but it won't be scalable for real world ID usage, because, for example, if you rename a function in workspace, you really want your IDE to rename this function across the whole workspace and not only the current crate. And you really you don't want to like restart your language server when you switch between the two crates. And sometimes you want to refactor across several crates simultaneously. So for Rust Analyzer, it is pretty important to view the whole graph of crates at the same time and view them in terms of like source code and not rlibs. Because again, like in theory, we like can compile all the crates except the current one to rlib, because we cannot compile the current one to rlib because we actually need to work with sources. But again, this breaks if you kind of like have two files open side by side from different crates. So fundamentally, the memory usage of Rust Analyzer needs to be higher than that of Rust C, because Rust C uses one crate and Rust Analyzer has like the whole graph of crates. And for Rust Analyzer, it's like, I think about 200 crates at the moment. The second reason why we use so much RAM is that, in theory, how an IDE should work is that it should like compute some information, then cache this information, and then store the cache on disk, so that it is not kept in RAM unless it is like really needed right now, and that and that IDE starts working much quicker after restart. And the core idea is like storing persistent caches on disk. Rust Analyzer internally has a lot of caching, but all the caching is in memory. We don't ever write anything to disk, and we only read the source code from disk. We don't have a way to persist caches yet. And that means that we cannot, for example, like process standard library and store less useful bits of it on the hard drive. We need to keep the whole thing in memory all the time. This is implemented this way for kind of like two reasons. First reason is that implementing persistence is like a really bad kind of worms, in that anytime you talk to operating system, you do any kind of like disk IO, there is a possibility of errors and you need to account for it. There is also a possibility of kind of like version skew, when, for example, the cache was written by one version of Rust Analyzer, but you are now running the other version of Rust Analyzer. There is also a possibility that the state of the cache diverges from the state of the files in the file system. Because, for example, you can open Rust Analyzer, it caches some things, then you close Rust Analyzer, then you edit files, then you open Rust Analyzer again, and you see that files and cache are inconsistent. So we deliberately cut this feature to keep Rust Analyzer as a simple, pure function which doesn't do any I/O, because that allows us to focus on interesting problem on how to actually cache Rust code. What strategies do we need to use to be able to not recompute everything when you type an X character? Separate these interesting problems from like more trivial problems of like dealing with mutable state and all that imperative world. The second reason why we don't do caching on disk, persistent caching, is that it is kind of like a very cheap way to like get some performance, especially during the startup time. Like, hey, like startup time is slow, so I will just cache things. Because we don't have this fast solution of just caching things, we actually need to put more effort into making Rust Analyzer itself faster, so that the startup performance is at least bearable. And it is kind of like okay ish, at least if you are working on the larger projects for the long amount of times. There certainly is a problem with certain parts of using Vim editor when you kind of like open and close editor all the time, and each new instance of editor creates a new instance of rationalizer process, and that itself needs to do this initial analysis from scratch, and this is like super frustrating because basically every time you open a new file, you need to wait for 10 seconds. That's a hard problem. I don't know. I'm not too familiar with Vim. I hope that it can somehow be solved on like the Vim side to make sure that the connection to the server is persisted. But yeah, other than that, this wait is like definitely bad, but it does not completely crush the user experience, hopefully. Well, at least for me. I am not happy, but yeah, good enough to work on rationalizer itself. Yeah, so I guess these are 2 or 3 reasons why rationalizer takes so much RAM. Unlike compiler, it keeps everything in memory. Unlike compiler, it works from source code and not from compiled RLibs. And unlike other more mature IDEs like IntelliJ Rust, Rust Analyzer does not persist its caches to disk, so it has to keep them all in memory all the times. And while we are at it, actually, let me tangentially share one trick we use to optimize memory usage. So one of the most costly data structures in Rust in terms of memory usage is the syntax tree, because in Rustalizer syntax tree, we want to have all comments and all white space. We want the syntax tree to be full fidelity, and that means that it is generally a heavier tree than a classical abstract syntax tree you see in the compilers. And the way that we handle this problem is that we make it easy to create and destroy trees. What I mean by that is that in general, Rust Analyzer keeps only like 100 most frequently used syntax trees in memory using LRU cache. And if it needs to process some other file, which is not currently parsed, it destroys some of the old trees and parses the file from scratch and uses its tree, which in turn can be destroyed later and then reparsed. So Rustalizer can reparse the same file several times during its lifetime, which allows you to like only keep the absolutely necessary syntax trees in memory, and that itself is possible because syntax tree very deliberately store all information about your syntax. Usually, in typical compilers, you decorate syntax trees with all kinds of semantic information, like the name resolution, types, and whatnot. And that means that you cannot actually destroy the tree because it contains so much useful information that by destroying the tree, you basically need to recompute the whole type inference from scratch. In Rust Analyzer, we only store syntactic information in trees, so the reparsing operation is comparatively cheap. I guess that answers the question about memory usage. Well, I guess not, because what does this mean in practice? Yeah, in practice, I think that means that you will need at least a couple of gigabytes of RAM to work with Rustalizer for the foreseeable future. Although in long-term future, we absolutely want to be more aggressive about working from on-disk data. Next question. Is Rust Analyzer currently multi-threaded in any way? What could be made multi-threaded? Rust Analyzer is actually multi-threaded. So there are, I think, two big bits which are parallelized at the moment. First is the initial loading of files. We use the awesome walk decrate by Burn Sushi, which allows us to traverse directories with source file in parallels and load all those files in memory using all of our cores, which is helpful. Another bit which is parallel, and let me just show it because why not? Symbol index Rayon. Yeah, it's the symbol index, and you see by the Rayon. Why the font is small here? I think I've increased it before. And as you see by the presence of Rayon, this is indeed parallel. So what this module does is it powers this workspace symbol feature, which is a fuzzy search across the set of all symbols. And the way it currently works is that we, in parallel, parse every file and doing some kind of like MapReduce scheme, collect the symbols from all the files into a single finished state machine. And finished state machine actually also is implemented by Burn Sushi. So yeah, this bit is parallel. Another thing which is concurrent but not necessarily parallel is our handling of language server protocol requests. Yeah. Syntax highlighting like takes a time to kick in because there is like this initial loading, and also because there is this annoying bug in or like kind of like design limitation, whatnot, in the implementation in VS Code, when it might be the case that if VS Code did not receive syntax highlighting immediately, it does not requires highlight information later. So you don't get highlights even if a Rust Analyzer can internally compute them. So this giant pull dispatcher thing is a structure which takes a language server protocol requests and executes it. And for almost all requests, we actually execute them on thread pools. So the general architecture of Rust Analyzer is that there is like this main loop, which is called main loop and is situated in the main loop module. And what this main loop does is that it's basically like a single threaded game loop, which accepts a request from the language client, processes it as fast as possible, and becomes ready to process the next requests. And to handle processes request as fast as possible part, we schedule all the actual work on the background threads. So what this main loop does is like JSON parsing, sending futures to other threads, selecting over a set of channels, because we like can get the other requests from the client, or we can get the result of the background task, or we can get notification from a file system about file system change, so we need to process it. And another bit which this loop turn does, which this main loop does, is processing modifications. So when you type something in a file, the thing which Rust analyzer needs to do as fast as possible is to acknowledge your changes. If, for example, there is like a syntax highlighting in the process, you really should not wait for that syntax highlighting to change, to finish. You need to apply the newly typed text as fast as possible. So this always happens on the main loop. And to do that, we actually like cancel all the background tasks. Then we get mutable access to the state of the code. We apply modification in place, and then we schedule like background tasks like highlighting using the read loop. So the core bit here is like using this Rust exclusive shared access, so that only the main loop has exclusive access and on the main loop applies modifications. And also having this cancellation system, which allows us to not block the main loop until the processing in the background thread finishes, but to actually like actively cancel the background thread and proceed with modifications quickly. And if we get back to this dispatcher threads, we can see that certain high priority queries are actually handled on the main loop as well. These are like the kind of queries where like the user really needs to get the response quickly, so it does not make sense to schedule them on the background thread. And one example here is like this. Let's match over something stupid. And if it is stupid, we print something stupid. Yeah, no, let's print something smart instead. Yeah, and so if we invoke join lines command, Rust analyzer join lines, we see that Rust analyzer like produced not this code, but this code. It smartly removed the curly braces. And this is the example of feature which needs to be at least somewhat smart. You at least need to be able to parse the source code to understand that, like, hey, this is actually like curly braces and not parts of string literal or whatnot. But it also is a query which is kind of like blocking the user, because like when you press join lines, you don't really want to wait for this like background thread to finish someday processing the request. So for this kind of queries, and there are like only a handful of them, we do on the main loop processing. Actually, I forgot what question I was answering, but and got carried away a bit with discussing the general architecture. Yeah, is Rust analyzer currently multi-threaded? Oh, and I haven't finished answering it yet. Okay, so we are parallel for indexing and for initial file loading. We are concurrent for actual request processing. Another thing where we really want to be parallel is actual analysis. So for example, when you load new code for first time, we process like standard library and all dependencies. And ideally, we would like to process dependencies in parallel, at least as far as it is possible. And currently, we don't do that. Currently, we process everything sequentially. I did some experiments with like parallel processing, and it actually like gives a certain amount of speed up on some benchmarks, but due to certain internal limitations, it is not as efficient as possible. Basically, we bottleneck at like 2 cores. And internal limitations actually kind of related to this optimization of nodes keeping trees in memory. In that, if you are doing processing in parallel, you can get into this like really bad situation where like one thread processes something and kind of like uses the tree and like then destroys the tree, But when another thread comes in and wants to work with the same tree, so it like resurrects the tree, and that's kind of not really scalable. I have a work in progress branch which should remove this internal parallelization bottleneck somewhat, and which should allow us to make actual analysis more parallel and hopefully faster. But as the refactoring itself is not done, I cannot actually tell if this would be as efficient as I would hope. So yeah, the general idea is that we really try to make like everything parallel, at least in theory, and it is somewhat parallel in practice, and it definitely is sync. Like there are no code in Rationalizer which uses something which is not shareable because we already are concurrent. It's just that if you naively add parallelization, which you can do, you will hit synchronization bottlenecks, which would prevent you from actually taking advantage of all the cores you have. Next question. The question is about 2015 edition, specifically that Rationalizer currently does not really handle edition 2018, 2015, the old edition, and like what are the plans regarding that. Yeah, in general, for simplicity and for the speed of development, we currently only support like the latest version of compiler, the latest edition, the latest version of VS Code, because Rationalizer still is kind of like experimental project. And the main idea here is to like figure out how to write incremental compiler for an IDE, and then actually make this a real product via this separate library effication effort. So that's like the reason that we don't fully support edition 2015. Certainly, the end goal is absolutely that Rationalizer like is a Rust compiler and supports the whole range of options of Rust C, including support for all editions backwards compatibly. So we will get to that one day. I'm not sure that we will be able to get to this soon. Is that, I don't know, maybe I am mistaken. But one thing we like optimize for is like impact on the users. And to me, it seems like support for edition 2015 is not that impactful, because it seems to me that most of the code is actually edition 2018. Maybe like I'm wrong, because I have not like actually made any kind of measurements or askings around this, but that's my general feeling. So I personally don't see put an effort into supporting 2015 more worthwhile than, say, putting effort into making Rationalizer loading faster, or using caches, or being more parallel. But once the kind of like more pressing issues are resolved, we certainly want to implement this edition support. And actually, I think it would be interesting to see what specific parts of edition 2015 are causing trouble. And it might be the case that actually supporting them is like not that hard, and it would be fine to like just make this work and whatnot. Yeah, let me now make a quick, really short pause to sip some tea and check out the questions on YouTube. So I'll mute myself so that you don't hear me drinking. Okay, took me a while to find the YouTube link, but apparently, unless I'm missing something, there aren't many questions in there. One is the question about proc macro support and IntelliJ. And yeah, that actually reminds me that I wanted to dive deeper into the work that Edwin has been doing on proc macros. So it's a good occasion. Yeah, let me start from afar by saying that proc macros is horrible for IDE writers for kind of like many reasons. But one of the most interesting of the reasons is that IDEs need to be really resilient. What I mean by that is that IDE by definition works with code which is incomplete and often broken in a curious ways. So for example, I would guess that Rust Analyzer sees much more broken code than Rust-C, because you usually invoke Rust-C when you kind of like hit save, or just like invoke it on the command line, or in general in kind of like you think like you are in a valid state and it makes sense to try to compile the code, and maybe this time there won't be any kind of error check errors, but of course you are mistaken and you have a 100 variable does not include enough errors to fix. Nevertheless, compilers in generally look like at the reasonable code. IDEs, in contrast, look at the code during the process of writing, during this intimate moment of creation, and you all type all kind of like horrible stuff, like, I don't know, an opening curly brace. This is like really horrible because like destroys syntax tree completely. There is like no any kind of hope to make incremental compilation here work, for example. But yeah, IDEs has to deal with that. And that means that actually IDEs kind of like hit more bugs or hit more corner cases. And that comes to a second problem. Let's say compiler hits some like really weird situation. Compiler actually can just like crash and burn, and it wouldn't be a big deal. Or it can actually go into infinite loop, and it also wouldn't be a too bad problem, because as a user you will just like kill the compiler using Ctrl+C, then like fix your code, because it usually the erroneous code which throws compiler into the loop, and then rerun the compiler and be happy. This is absolutely not true for the IDE, because IDE is a long-running process, and like if your IDE goes into a loop, like you cannot like easily kill it, and if you kill it, it will take some time for an IDE to like start again and like restore the caches, even if the caches are restored from disk, and help you being productive again. So yeah, the problem here is that like compiler like generally looks at okay code, and it can just die on bad code. IDE, in contrast, looks at all kinds of weird source code, and it also has to be alive at any moment in time. Like IDE cannot just die on the user. IDE needs to be somehow resilient to errors. And that is a specific problem with proc macros, in that Rust-C currently just loads proc macro library into Rust-C process and like executes it as a dynamic library. And if proc macro aborts or goes into infinite loop, so does the compiler, and it is not a problem. But for Rust Analyzer, if a proc macro dies, then the whole IDE process dies, and that is kind of bad. One of the design questions for IDE support in Rust is how do we actually like run procedural macros in the IDE context? And the solution, which was prototyped in IntelliJ by one of the IntelliJ developers, is really, really smart. The idea is that instead of loading macro into the IDE process, we write a small Rust shim which links to the macro and which spins this separate server, separate process, and then IDE uses IPC communication to communicate with this process. And if process for some reason dies, well, it's no problem. IDE can just restart it. Yeah. So the primary approach here is reliability, in that you just isolate proc macros into a separate process and you no longer need to worry if they crash. And they will crash because IDE will run them on a completely incomplete code. And if IDE can be reasonably expected to deal with incomplete code in a sane manner, it's totally valid to expect proc macros to just die on incomplete code. The second benefit of this approach is organizational. Currently, the proc macro API, like the API of proc macro dynamic library itself, is a total implementation detail of Rust-C. And you need to basically use Rust-C private permanently feature to use proc macro code. So by separating this proc macro shim into a separate process, we actually can make these only like small parts of our IDE code base to depend on the nightly features of Rust. And that is kind of nice because bootstrapping from Rust-C is like painful and is actually one of the like main design goals about Rust Analyzer as a project. Like Rust Analyzer is a simple Rust crate. It is built with cargo build on stable. There are no any kind of tricks. There are no nightly features. It is just Rust code. And that actually helps to speed up development of Rust Analyzer itself considerably because everyone knows how to do cargo check and you don't have to wait ages until XPY does like everything. Yeah, so that's the general idea about procedural macro support is that we load them in external process, and this external process is a fault isolation boundary. And then we communicate with it via IPC. And Admin works exactly on this, except that they had another hilariously brilliant idea to how like not use nightly features even in this like small proc macro shim. Basically, the idea is like copy paste the part of the compiler which implements the proc macro server and just remove all nightly features from it. And it actually like works. Of course, it like relies on the implementation details of Rust-C, of implementation details of binary ABI of proc macros, but still we are able to get something working using stable Rust, and that is a huge big deal. Of course, long term, depending on nightly APIs on stable is never going to fly. So we will have to invent a proper solution there. I am not sure what the proper solution would be, but I'm actually really, really hoping for these WASM proc macros proposals. Because if you actually run proc macro in WASM VM, that means that you can run it in process because WASM VM is a natural sandbox. it cannot abort, it cannot deadlock, it cannot go into infinite loop, because you can always shut it down from the outside. So hopefully long term, we will just use this Proc macro sandbox inside IDE, which will be an isolation boundary for Proc macros. And let actually me remind myself what question I'm answering. Oh, it was some question from the IDE. Yeah, like what is the relationship between Proc macro support in IntelliJ and Rustalizer? Yeah, we just use the same approach which IntelliJ Rust implemented first. I don't think they actually kind of like made it into production yet, but we definitely made a first working proof of concept, and it's like hugely helpful, and definitely they get all the credit for this idea of and this implementation of Proc macro as an external server. Okay, I see that actually questions kind of died out, which is actually really convenient, because it's almost 2 hours and it's time to say goodbye and probably even see you next time. If there is interest in repeating the things. And as another reminder, again, we have this awesome Rust experts service, and if you want to like talk to Ferrous people like me or James, you can use the service, and we probably can help you write more Rust better and be more productive. Okay, I guess stop sharing and waving goodbye. And thank you everyone who asked questions, who participated. It was hugely interesting for me to actually share these things I know and to see what questions are interested in. And in general, it's just been super fun. So thank you very much. Goodbye. Stop live